All right, hello everyone. Welcome back to Historical Geology 1404. Today we are starting on lecture 6. We are well into module 2 at this point. I went through and graded everything yesterday. So your grades as of right now should be up to date. And I am going to be, for those of you that are in high school, I'm going to be submitting your next grade report this coming Monday. Okay, so whatever your grade is as of Monday is going to be what is reported to your high schools. Next Monday, yeah.
I still don't have to. I hate my roboto there. What are we doing that class?
That has been graded?
Yeah, like, nothing's been graded. My grade's still NA. Swear to God.
That might be because the calculator is off. Bless you. That is something I need to check because every now and then, whenever they do an update on Blackboard, the grading calculator is off, and it has all of the grades, all of the points associated to assignments that don't exist. Like, I have all of the labs categorized as lab, all of the discussion boards categorized as discussion. But whenever they update Blackboard and they add new things or take things away, sometimes it'll reset my grading scheme so that it gives all the points to the assignments category, and I don't have anything in the assignments category. It's all labs or discussion boards. So I'll go in there and see if that's what happened. Is anyone else seeing that? You don't actually have a grade right now?
I don't have a grade.
Then that's exactly what happened, and that is super annoying, and I wish they would fix that. But I've already complained about it 100 times, and it's not going to happen. All right. Change grade scheme. I'll do that after we're done with lecture today. I'll do it during lab time. It takes me 10 seconds. I wish that they would even just tell me at all when they update the system, so I would just know to go in and do it, but they don't. Okay. Good to know. And if any of my online students are panicking because you're in the same situation, don't worry, I'm going to fix your class too. What else? Any other questions or concerns? No? We had a few strong earthquakes over the weekend. Not here. I said we. I meant the royal we, right? On Earth. There was a 6.3 in Afghanistan and a 6.1 and then another 6.0, I believe, in Kamchatka, Russia. You guys remember earlier this year when there was that super powerful earthquake in Russia that set off that volcano? I told you about it in 1403. It's that same region. They keep getting shook up, so nothing too unusual there. You would just move. It is good that you are that flexible, but most people, I don't know if I could say most people, a substantial number of people are not as flexible as that. If I told you that there was the potential likelihood that something would destroy your house and potentially kill your family here, how many of you would move? A lot of people. You wouldn't?
Yeah.
Oh, you would? Oh, okay. Yeah, it makes sense that you would. However, if that were true of everybody, would the death toll in New Orleans after Hurricane Katrina have been so high? No. Would 58 people have died in the Mount St. Helens eruption? No. If everyone felt like that, if everyone decided to act upon that, then of course there would not be any deaths from these things that we can talk about, or these things that we can, these things that you learn about in my class. Okay? Okay. Any other things that we should talk about before we get started today? No? All right.
We should watch The Martian.
We should watch The Martian? Ooh. Why? I want to know the reasoning here.
Good movie.
It is a very good movie. I cannot contest that. It is a very good movie.
I watched it for the first time in a while this weekend.
Oh, you're gonna?
Huh?
You're gonna watch it?
I did this weekend.
Oh, you did this last weekend. Nice. Yeah. Very good movie. I absolutely agree it is. Not, I mean, it has some relevance to the things we talk about here, but it's not super relevant. So this week I am actually here. I'm going to do this also during lab time. I'm going to send out the Google form for movie night. Google form. Movie night. Yeah. I'll set that up and send it out here today during lab time.
The options for it so we can get thinking.
Jurassic Park is on there. Ice Age is on there. Yeah. Yeah, there's a couple of different options on there. All right. If you guys have any other ideas for relevant movies that could go on there, that is things that have to do with fossils, the history of life, things like that, please let me know. Recommend them. I'll throw them on there if I think they're relevant. It is not relevant. No. No. Paranormal demons, not relevant to the subject of the class, unfortunately. All right. All right, let's jump in. Today, lecture 6. We're talking about environments and life. Last time we talked about diversity of life. I gave you a brief introduction to all the various different forms that life takes and has taken and how life can change. How do we learn that life can change? How do changes occur in life? I mean, sure, getting older, but that's an example of something called ontogeny. That happens to you. That doesn't happen to your species.
Because of like DNA and mutations. We evolve.
DNA and mutations. Okay, evolution is a product of the mutations that occur to our DNA. How do we get those mutations?
Radiation.
Radiation. Radiation does what? It affects the chromosomes in your DNA, knocks them out, changes them, adds some energy. Changing the recipe, changing the code in your DNA to yield a different result. Now, I want to just re-emphasize, rarely does that equal a change in you. And when it does, it's usually through sickness. For example, overexposure to radiation can give you cancer, right? That is one example of a mutation that your body can experience that will affect you. Most of the time, though, mutations that occur to your DNA will not manifest in you. They will manifest in your descendants. So I, this morning, on my way into work, could have been struck by a particle of radiation at just the right place, hit my DNA in just the right time, that any future children I have might be born with one eye. Possible. Statistically low, but possible. Okay? Could happen any day as well. You don't know what mutations you've experienced in your lifetime. You're going to experience some of them. It's just that some of them won't make a difference. Some of them might, but others won't. Okay? Cyclops, right. That was just an example, okay? Unfortunately, what does this mean for superheroes? This means that our common fiction of superheroes, becoming a superhero by falling into a vat of toxic waste or getting hit by a radioactive burst of gamma rays, that does not change you other than killing you. It very likely will kill you. What it won't do is change you into a superhero.
What about the radioactive spider?
Radioactive spider probably will also kill you. And the radioactive spider would probably be dead in the first place. Okay? Now, what does this also mean for, you know what, let's keep talking about superheroes for a minute. Who doesn't like talking about superheroes? Speaking of superheroes, did you guys see that DC is up for sale? Yeah, they're selling DC right now. Yeah, Paramount has made, I think, 3 offers on it, and each one keeps getting refused. I don't remember what the offers are. A lot of money, though, billions of dollars. And then Netflix just threw their hat in the ring. DC has a lot to it, yeah. And whoever has DC is in direct competition with Marvel, right? So there's a lot of potential there. If you can pop off harder than Marvel can, they've been doing pretty poorly. It might be a good opportunity. James Gunn doing what he's doing right now with the DC is a legitimate threat. And now whoever buys it is going to inherit that potential threat to Disney. So at this point, I'm just waiting to see when Disney puts their offer in. The only problem with that, it might be someone could, I imagine someone would probably try to submit a monopoly lawsuit because DC and Marvel represent the 2 big houses of superhero fiction right now. And if you own both of them, someone might contest that as a monopoly over a franchise, which monopolies are illegal, so. All right, but anyways, coming back to the topic of superheroes, if there was a mutation, what could it do? it could only work within the bounds of science. Will there ever be a person who can shoot lasers out of their eyes? No. Why? Because that is not biologically possible. There is no mutation which would allow that. Okay? Could someone fly? Only if they can fight the laws of gravity. There is no mutation that would allow that either. Okay? So, there are a few things that you could do. We will talk about this. If not today, then next, probably on Thursday, we'll talk about ways that we can change DNA to suit certain needs. For now, I'll just leave you hanging on that one. Alright, so let's talk about why life adapts in the first place. Why does anything change in the first place? Why does metamorphism happen? Why does weathering happen? Why do all of these concepts we've learned about for weeks now, why do they happen? Huh? Tectonics is a small aspect of what I'm looking for here. New climate conditions is an aspect of what?
Why we adapt?
Yes, but I'm asking why anything changes, let alone us or life in general.
Oh, because time goes on everything. Yeah, it's time.
There's a change in what?
Everything.
In the environment.
Environment! There we go, that's the word I'm looking for. Anything, all will change because of a change in the environment. The places that we've talked about that don't change much, the moon, for example, there is no change in the environment, and so things don't change much. Mars, very little changes in the environment, and so very little changes to Mars physically. Here, stuff is changing all the time. And so naturally, we see a lot of changes here. Weathering, erosion, evolution, all of these being an example. Tectonics, too, sure. Okay? So we see a change in the environment. This change in the environment sparks a change in the things that are in the environment. Life, for example. Some things that can change in your environment that might cause life to need to change. What if your food source runs out? What are you going to do? Jackson, if you couldn't eat any more ice cream cones, where would you go? What would you do?
Make ice cream?
You would make ice cream? Oh, it sounds so easy. Or would you go somewhere with ice cream cones?
Oh, yeah.
Right, so this is what a lot of things will do. Very rarely do things in nature have the ability to make their own food source, right? A bear just can't go out and make honey or salmon. They have to go where the honey or salmon are, if that's what they eat. Okay? So what's this called? What is it called when animals will move location following a food source? Migration. Good. Migration is an example of life adapting. Migration often happens because of changes in season, which change food conditions. You might also see migration as a result of a need for breeding. There are certain species that only breed in certain places. Whales, birds, what was the other one I was just thinking about? Oh, there was a third one that I was just thinking about, and now I can't remember it. But there's a lot of things that will... Oh, fish, salmon. Salmon will go upstream in the American Northwest to breed upstream and then leave, or die, depending on the species, to go back out to sea. Okay? My grandparents used to live out there. We would go and watch the salmon runs. I'm talking millions of salmon swimming upstream to get to their breeding grounds. And then a few weeks later, it would smell terrible because there were millions of dead salmon bodies washing back downstream after they finished their breeding cycle. Okay? Huh? How are the dead ones? Well, we try and find the ones that weren't that old, and then we would cook them up and eat them. It was delicious. Okay? Have a good old salmon bake.
Yeah, but salmon gets really stinky when you cook it.
Salmon gets...
Stinky,
It gets stinky, yes. They are stinky fish in general. That's very true. Very rich in omega-3 fatty acids, though. Very good for you.
Yeah, my
Okay.
sister likes them a lot, but my mom tells
Bless her.
her not to eat so much because they're too gangrene.
That depends on the food source that your fish have had, where they're from, and how polluted their water is. But yeah, that's a possibility. It's like you'd have to eat a lot of fish to get that, though. The reason why mercury poisoning is so something that's really emphasized is particularly for pregnant women, because if you eat some fish that might have mercury in it, that mercury will probably end up in your placenta, and that placenta will pass it on to the child, and the child can have physical deformities as a result of exposure to mercury. It's very rare for someone to eat enough fish to get mercury poisoning on their own, though. Right? Okay, so your change in food source is one example. Someone mentioned a change in climate. Under what circumstances would a change in climate cause life to adapt? Right, sure, seasons changing. Are we experiencing a seasonal change right now?
Yeah.
How many of you were chilly this morning?
It was a little bit cold. But not very.
I'm seeing a lot of sweaters out there. Be honest with me. How many of you were chilly this morning? Weak. I'm kidding. No shame. Okay, no shaming here.
I mean, I do wish it was a lot more chilly.
You wish what?
I wish it was a lot colder.
You wish it was a lot colder? Just you wait, Henry Higgins. It's coming. All right. So yeah, we're.
Snow.
Huh?
It's got to snow.
It's gonna snow? Well, fingers crossed. So I was about to say I want my kids to have a white Christmas, but we're gonna be up in Idaho anyway, so they're pretty much guaranteed a white Christmas. My parents live in northern Idaho. They're about as close to Canada as you can get while still being in the United States. They live way up there. We haven't taken my kids to go visit their grandparents in about 4 years. My two youngest kids have never been up there. So I know, because they're 4 and 2. Almost 5. She's turning 5 next week, and newly 3. So almost 5 and 3. So they haven't really been up there, huh?
What's your oldest?
He just turned 7, so he's been up there when he was a little kid. But it's been a while, and so we felt like it was a good idea to take them up there for Christmas this year. So we're going to be there, but they're going to get a white Christmas. Hopefully you guys get a white Christmas down here too. But regardless, coming back to the subject here, a change in climate is going to cause a change in life. Life will have to adapt to that. Now that doesn't just mean the cold, my friends. This also means chemistry as well. Ocean chemistry being one example. What might cause ocean chemistry to change? Sea level associated with that, yes, because rising sea level means you're doing what to the water? You're adding more water, and that adding water is going to dilute, say, how much salt is there. Right, so you might see a change in salinity as a result of sea level change. That's a good thought. But there's also another thing I'm trying to remind you all about. What else might change the chemistry of ocean water? What kind of pollution? Huh? I mean, yeah, so all pollution will for sure. But there's one particular greenhouse gas I'm looking for that we spit out a lot of. Carbon dioxide. Carbon dioxide. Carbon dioxide in the atmosphere, some of it is going to make its way into the ocean. And that gets incorporated into the water and makes what? Do you remember what happens when we dissolve carbon dioxide in water?
It gets rid of the dioxide and just the carbon.
So we are definitely going to see a change in chemistry. But what I'm talking about here is the resulting equation or the resulting chemical of dissolving carbon dioxide in water. It makes something we learned about called carbonic acid. Yes, this is ocean acidification. The more carbon dioxide gets dissolved in my ocean water, the more acidic it gets. The more acidic it gets, the more hostile it is as an environment to the organisms that live in there. Not just because the organisms are breathing it in. Like what would happen if I increased the acidity of the air you breathe? It ain't going to be good for your lungs. Right? It ain't good for the gills of whatever's breathing it underwater. But also, the shells. What mineral dissolves in the presence of carbonic acid fairly easily? What do you got, Kevin? Calcite. Calcium is the element. Calcite is the mineral CaCO3, which has calcium in it. Good. Calcite. And most minerals that live in our ocean use calcite to make their shells. This is going to make a very bad situation. Life will need to adapt or die. Okay? Temperature changes, moisture changes, these are also relevant. Okay? What about predation? Can you think of a super predator, an apex predator, that has caused massive changes on the face of our planet? Were they all predators? No. Open minds, open minds. What is an apex predator that has caused incredibly massive changes to the environments on our planet? It's you, Remy. Yeah, I'm looking at you. You're an apex predator. Did you know that? Do you feel like an apex predator today? No? Well, you are one. We are the apex predator that has caused the most changes on our planet. Lions, tigers, bears, oh my, they haven't done anything nearly like what we have. The Tyrannosaurus Rex was killing and eating stuff for millions of years, and they didn't cause nearly as much change as we have on this planet. Okay? We are the predator that has caused the most change, and the most change that life has needed to adapt to. And we start to see how life is beginning to adapt. Do you remember I told you about the herd of elephants last week? What was unique about this herd of elephants I told you about? They had no tusks. Why is that relevant? Is that an advantage? Really? People poach them for tusks. People, our species, not you and me. I hope not, right? None of you have gone to Africa to poach, right? I sure haven't, right? Matter of fact, Kenya has a military unit specifically for shooting poachers that they see, right? These people rove around Kenya and actively engage in warfare with the poachers, okay? But there are members of our species that do target these things, these rhinos, these elephants, specifically for a piece of their body. And these elephants without tusks have adapted. This random mutation caused an adaptation that gave them an advantage, and now here we are, right? Life has to adapt to us or die. We are an aspect of the environment as well. Same thing with competition. What if someone else starts eating your food source? Well, you need to adapt or die. What if your habitat changes? Adapt or die. Your rainforest goes away, right? Adapt or die. This is what it comes down to, my friends. You got to adapt or you die. Adaptation sometimes means leaving, or it means changing the way you interact with your environment.
Also, like how we get rid of a lot of animals in environments, so they either die or they go somewhere else.
Right. It doesn't seem harmless to cut down one tree, does it? How many bugs and birds and squirrels live in that tree?
That one tree? Probably not.
Millions.
Not the ones in my house.
Millions. And when you cut down that tree, you're removing an ecosystem, and everything that was living in that tree will have to move on or die. What happens if you cut down the whole forest?
That's like billions and trillions of them.
Trillions, yes. It's sobering when you put it in that perspective. Everything we do in our environment has a consequence. For every action, there is an equal and opposite reaction, right? We've all learned the laws of physics, I'm assuming, at least to some extent, right? Every action we do has a consequence. Okay. Now, ecology is the study of these environments. And as a branch of that, how changes in those environments will cause changes in the organisms that live in them. Okay? A niche is a word that we use to describe, think of it as a pocket in that environment, okay? And how it is filled, a role that is filled in that environment. For example, dolphins fill the same niche now that an animal called an ichthyosaur did early on in the time of the dinosaurs. They look nearly the same. I'll show you pictures of them later. And they fill the same niche. They both eat approximately the same things. They behave in approximately the same ways as far as we could tell, right? There are animals in North America that fill the same ecological niche that animals in Australia do, even though they're on different continents. Okay? This is how it works. A niche, think of a niche as an apartment in a building. Every apartment needs to be filled for my environment to function. Every niche needs to be filled. When a niche is left vacant, something else will adapt to fill it. Okay? Because that apartment, it's always got to be filled. A population is a group of individuals within a single species in a given area. And a community is a group of populations in a habitat. What does that mean? Here in this classroom today, we have a population of humans, and a population of snakes, and a population of bugs. Right. We are, all of us, a community within the bounds of this classroom with at least 3 given populations, each of which is filling a niche. You all are filling the niche of living in these tables. You all are filling the niche of living in those tables. You all are filling the niche of living in these tables. Okay? Each of us occupying a separate space, performing a different function within that ecological unit. Okay, so these are some of the terminologies you'll need to remember that I'm going to use from now on. Niche, community, population. This is what they mean. Okay? We're going to talk a little bit about some of the environments around the Earth and the ways that they change and how it affects the ecology that inhabit that area. Okay? You'll notice that there are different bands of environment around the Earth. Rainforests tend to be around the equator. Then there tend to be slightly drier areas on either side of that, and then deserts on either side of that until we reach a certain latitude, north or south, and then we return to a different type of forest, not a rainforest type, more of a deciduous forest. Okay? And then above that, it gets too cold for any major plant life. That's where you get things like your permafrost and your high steppes, grasslands, and things like that. All right, starting with our atmosphere. What do you know our atmosphere is made out of?
CO2, oxygen,
CO2, nitrogen.
nitrogen.
Nitrogen sure is on there. 78% of our atmosphere is nitrogen.
Oxygen.
Yeah, oxygen is on there. About 7%, or 21%, excuse me, is oxygen. What's the other one? Well, remember, CO2 is mostly oxygen. 1 carbon, 2 oxygens. This ratio of oxygen, this percentage of oxygen, takes into account loose oxygen that we breathe, but also CO2. Okay? This is by mass count, okay? Not by molecule. Okay, so what's the other one? The other 1% is mostly argon, which is a byproduct of the natural gas and seeps. Argon is something that kind of naturally seeps out of the ground and up into the atmosphere. There are actually a few places in the world where the argon concentration coming out of the ground is so intense that you have to have an argon detector in your basement, or else you could walk down there and instantly suffocate because of how much is leaked out into your basement. Yeah.
So what happens if it does get in your basement?
You have to get it vacuumed out. You got to pay someone to come vacuum it out. All right. Now, what function does the atmosphere have as far as affecting our environment? The concentration of greenhouse gases in our atmosphere is going to influence how much energy, solar energy, stays in our atmosphere and therefore transfers into you and me and everything else on our surface. Okay? Remind me, greenhouse gases. Do you remember what I told you a greenhouse gas was?
Like
CO2 is an example, but what is a greenhouse gas?
like made gases or something?
Huh?
Like gases that were like made or
No, they're not man-made gases.
Gases made through radiation.
They're not gases made through radiation either.
Is it like from the atmosphere?
They are in the atmosphere. A greenhouse gas is a molecule of gas that is so big it has the ability to remove energy from solar radiation. CO2, methane, there are several that we will find in our atmosphere commonly. Do you say methamphetamine? Not a greenhouse gas. But these hang out in our atmosphere, and the more of them there are, the more solar radiation remains here on our planet, and the less makes it back out into space. The greater the concentration of CO2 and other greenhouse gases, the greater the amount of solar radiation that remains here. We can see the effect that this has. We have an example in our solar system of what happens if this goes too far. Okay? When you get too much greenhouse gases in your atmosphere, then so much radiation stays behind that it heats up the surface of your planet so hot that it makes a never-ending cycle of releasing CO2 and other greenhouse gases, and that heat can never ever escape, and it just gets hotter and hotter and hotter and hotter. The planet I'm talking about is Venus. Venus is actually just right outside what we might typically call the Goldilocks zone. It's hot. It's always going to be hot. But Venus is extremely hot right now. I'm talking like 700 degrees. Huh? Because it is the victim of a runaway greenhouse effect. An unknown amount of time ago, possibly a billion years ago, possibly longer, possibly more recent. Everything okay? Okay. Something happened on Venus. We're not sure what it was, but something released a massive quantity of greenhouse gases into the atmosphere. Venus, before then, we might have been able to fly a ship there, and with special suits and special buildings, special habitations, we potentially could have lived there. It was probably just barely too hot for us to live on without technological assistance. Maybe maybe midday would have been 150 degrees instead of, what we have to deal with here. But that's something we can live with the right heat suits. Then there was this runaway greenhouse effect that caused a positive feedback loop in which more and more greenhouse gases were released, causing more radiation to remain behind, causing more greenhouse gases to be released, causing more radiation to remain behind, and it's a never-ending cycle. That's Venus. Could that potentially happen here? Absolutely. We would just need to release a massive quantity of greenhouse gases. Now, we have been for quite a while now, ever since the Industrial Revolution, releasing a lot of greenhouse gases in the atmosphere. Not nearly enough to cause a Venus-style effect, my friends. We would have to release a heck of a lot more. But enough to substantially start to change our ecosystem. That is why global temperatures are rising at a higher rate than they would have otherwise. We were already in a global warming trend. With or without humanity, Earth would already be warming right now. We have substantially increased the rate at which it will warm, though. We're already a few degrees hotter than we would have been otherwise. And by the time the year 2100 rolls around, we're going to be even hotter than that. Okay? It's going to be worse than it would have been. Okay. So this is what greenhouse gases do. Now, heat distribution on the surface of our planet is what makes climate. Why is the Antarctic covered in ice? Why is the Sahara barely ever wet? Why does it barely ever get rained on? Heat distribution. Okay? If we increase the amount of heat present on our planet, that's going to change the ways that heat is distributed here. Does that make sense? And that, in turn, is going to change environments. Other changes. Elevation change. This comes down to what? What can cause elevation of land to change?
Landslides?
Sure, very small. What's your favorite answer?
Tectonic.
Tectonics. Yeah, tectonics is the most common way that we will see elevation change. Through tectonics, mountains are raised. Through tectonics, plates are squeezed or stretched, creating lower elevation zones. Okay? So through these tectonic activities, we will see the development and change of new environments as well. Do we get higher or lower temperatures the higher up we go? Lower temperatures. Do we get more or less atmospheric pressure? We get more atmospheric pressure the higher we go? Atmospheric density and therefore pressure gets lower the higher you go in elevation. This means that you're going to see a change in the things that live in that environment. Okay? Also, how far am I from water? Why would water matter? Distance from water, how is that relevant to life?
Breeze.
Huh?
The water they get buried.
Everything needs water. Let's think about our food chain for a second here, right? You and me, what do we eat? Some of you are eating things right now. What are you eating? You're eating Pringles. That's a potato chip. That's based off a potato, a plant. What are you eating? Cinnamon Toast Crunch. There's a lot of artificial ingredients in that. But grains, which are a plant. What were you eating before? I saw you eating something before.
Ice cream.
Yeah, okay, ice cream. That comes from a cow, right, which is an animal which eats plants. What else?
Breakfast bowl.
A breakfast bowl, eggs, sausage, right? Animal products, and those eat plants. You gotta have plants, you gotta have water, you gotta have food, right? It's all part of the food chain, okay? All right, this band that you see in red here is what we can generally call a tropical zone. There are a few exceptions. There are a few deserts that extend into the tropical zone. There are a few rainforests that don't go all the way through the tropical zone, but it is around the equator, and that's where the furthest extent that we would find tropical zones, typically, okay? Then where you see this blue band overlapping the red one, we're calling that, what? I thought someone asked a question, okay? We'll call that a transition zone, okay? Where you have just blue, that's going to be a mainly desert zone, okay? So where they overlap is where you transition from one zone to another. That's where in like Africa, that's where you would get, say, a Serengeti or a grassland, okay? Savannas, okay, is a way that you can describe that. So the savannas are those grasslands. It's too dry to have a rainforest, but it gets enough water that you still have plant life. Okay? We here live in what you might typically refer to as that transition zone, verging into that desert zone. We aren't a true desert like the Sahara is, but we are close enough that we could call ourselves a desert. We are arid, a little bit more than semi-arid. That rainstorm we had the other day that shut down my event might cause some doubt there, but that is uncommon, huh?
So we're a savanna?
We aren't in a savanna, but we are in the same sort of band and latitude that a savanna would exist in, there are savannas further east of us in the southern states. There are savannas in Africa.
So then what would we be classified as?
We are a semi-arid environment. Not a true desert, but close enough that we could call ourselves a semi-arid desert. Okay, so this is what a savanna would look like. Looks not dissimilar to what we have here. That tree, we don't have those kinds of trees here. But if you replace that tree with like the odd mesquite, this does not look dissimilar to what we have here, except maybe we have a little less natural grass, right? We're a little drier than that. Then we have forests. There are two types of forests. You have your coniferous forests, like this, called coniferous forests because they are mainly made out of conifers, which have adapted to prefer colder environments. So you'll find these up north or at high altitude. Then you have temperate forests, like this. Oak trees, apple trees, sycamores, things like that. All right, so this is what you're going to find in places like Georgia. Yeah. Can you hold a snake? Sure. Can you pay attention at the same time? All right. Where's his head at? I can't even tell.
Right by your back.
He's what?
On your back.
He's on my back. All right, Jackson. I'm slowly training the new snake to be held, to be nice. Every time I hold her, she tries to attack me at least 3 or 4 times. But the more I do it, the more used to me she'll get, and then I'll eventually be able to let you guys hold her too. All right. Where was I? Oh, yes. Okay, so you'll find these in places like Georgia or North Carolina, or if you ever, okay, here we go. Drive through New England in October. So right about now, October, November, all the trees are going to be vibrant shades of yellow and orange and red. It's beautiful. Just drive through the Appalachians. It's going to blow your mind. If you ever have the opportunity, please do it. Okay? Then you've got tundra. Tundra is where, here, let me pull up a picture. Tundra is where it is so cold and there is not enough liquid water. What's what? Oh, I mean, yeah, that's what it's named after, right? It is so cold and there's so little liquid water that you cannot have most forms of plant life. Now, most of the time, what you do have are mosses. These are clumps of moss. They just live on the surface. They don't need very much soil. If only the top few inches of soil are unfrozen, the moss will survive. They don't even need that much water either. Okay? So this is a tundra environment. That's far north or far south. Okay?
So is Antarctica like a tundra?
The outer, anywhere, okay, so a tundra is not covered in ice. It is just so cold that most of the soil remains frozen like this. Sure, it'll be covered in snow seasonally, but not perpetually covered in ice. So Antarctica mostly is not a tundra, but there is definitely tundra around the outskirts of the continent, where it is not always frozen, okay, or at least not always under ice. Any other questions? I'm trying a new protein shake. I'm not a big fan. I like the other ones better. Okay. Let's talk about how we can interpret past environments. How do we learn more about it? Plants are extremely helpful for this. What do plants do? What have we learned, or what do you already know about plants that might help, that might allow them to help us as a tool for interpreting past environments?
Helping us with food because animals eat plants and we eat animals.
Okay, so knowing how they work in the food chain now could help us interpret how they might have worked in the food chain before, right? That's good. That's an application of what? What principle is that an application of? Yeah. Uniformitarianism. Physical, chemical, and biological laws that operate today also operated in the geologic past. So, by seeing how plants interact with ecosystems today and are incorporated into them, are a part of them, we can make reasonable assumptions for how plants could have done the same thing in the past. There's also this other concept, isotopes. We learned about isotopes. Someone remind me what an isotope is. When you take away neutrons or add neutrons, right? It makes a molecule, I should say an atom, that has a uniquely different mass than what it had before. And we can measure that against other things. So carbon-12 and carbon-13 are different isotopes of carbon. Which one is more massive? Which one has more weight? At least here on Earth. 13, it has an extra neutron. Oxygen-16 and oxygen-18 are other isotopes. Which one has more mass? Oxygen-18. Good. If I want to measure how much rainfall was occurring in an area, I can measure the ratio of oxygen-16 and 18. Why is that? Well, let me explain this. Huh? It doesn't have more density, but the extra mass means that oxygen 18 is going to behave differently when you make rain. If I have both oxygen 16 and oxygen 18 in the atmosphere, when water is precipitating into rain, which one is more likely to fall first? The one with more mass or the one with less mass? The one with more mass. Therefore, the water molecule, which has oxygen 18, is more likely to fall before the water molecule with oxygen 16. Therefore, the plants which absorb water containing oxygen 18 likely lived near the equator where the most rainfall occurred. Remember our convection cells of air circulation? The most rainfall occurs near the equator, and the further north or south you go, the less rainfall occurs. More oxygen 18 is going to get rained out at the equator than up north, which means that the concentration of oxygen 16 in my plants to the north and south will be higher. Wait, what? So I can look at the oxygen isotopes in a fossil plant and reasonably assume approximately where it was relative to the equator, just using that. Okay, well, what about carbon? Because carbon dioxide in the atmosphere has a higher concentration when temperatures are hotter, the ratio of carbon-13, which again is more heavy, in my plant is going to be relevant to general temperature of that area at that time. So carbon 12 to 13 helps me give an approximation for temperature. Oxygen 16 to 18 helps me draw an approximation for how much rainfall there was and therefore proximity to equator. I can use these isotopes to make these cool assumptions, and that's really what they are, assumptions. We can't be as specific as an X and Y coordinate, but I can make assumptions based upon what I see today about the location and environmental parameters at the time the plant were alive, which gives me relevance for a bunch of other stuff as well. If I'm trying to measure everything about an environment and I have a fossilized cabbage palm, I'm going to do all of this stuff to it, but also it's fairly safe to assume what other animals maybe were living in there as well. We know through previous discoveries, Triceratops were very fond of eating cabbage palms. So if I see a semi-tropical area with good, relatively warm temperatures and lots of cabbage palms, it's a reasonable assumption that there were probably Triceratops in the area as well. And I'm going to use that information as a paleontologist to go back to that layer of rock and look for Triceratops bones. Okay? All right, let's talk about marine environments for a second. What changes in marine environments, which means underwater, remember? Specifically under the ocean. There is constantly sediment getting washed out to sea. And that sediment falls to the bottom of the ocean. It gets incorporated into layers of rock that pile on top of each other, preserving evidence of whatever was going on at that time, right? We're going to see changes in the fossils that are present there, changes in the chemistry of the water that will be present there, changes in the way that the water moves because of the ways that the sediment is being deposited physically. This includes currents, okay? A current is determined by changes in both wind and temperature of water. And they changed a lot, fairly commonly actually, okay? In warm currents, you're going to see life kind of follow that. You guys ever watch the, what was it? Finding Nemo? Yeah. You remember how they went to find the EAC, the East Australian Current? Yeah. The EIC, you know? That was a current, okay? And it was traveling really fast along the coastline of Australia. That's just one example, okay? That's one way to look at this. I've got a map here. Let me pull this up. that shows you the warm and cold currents of water as they currently flow around our planet. Warm water circulating around the Pacific. Warm water here is circulating around the Atlantic. Down here in the South Atlantic. Over here in the Indian, right? But look what happens when you get further north and south. It cools off. Water that is moving from the south up north towards the equator is going to warm up. It's going to become a warm current. Water that's moving down south towards the equator is going to warm up. Water that's moving up north turns cold. This cycle is what promotes a lot of the distribution of salt in the oceans and the migration patterns of life in the oceans. If the currents change, a lot of other things change. For example, right here, where the Isthmus of Panama is, this tiny little narrow neck of land between North and South America, that wasn't always there, guys. It only occurred over, how long ago was that? A couple dozen million years at most, okay? I'll talk about this more later on. I have a whole slide dedicated to it. But that wasn't always there, which means that right here at the equator, there was communication between the Atlantic and the Pacific. As a matter of fact, it wasn't until that little narrow neck of land formed, cutting the Atlantic and the Pacific off here, that the Atlantic started getting colder and saltier. The Pacific remained warmer out here. Tides, also. Tides. What controls tides? The moon is the largest source, but it's not the only tidal force in our neighborhood. What's the bigger tidal force? The sun, yeah. So only about 60-something% of the tidal forces that influence our ocean come from the moon. If the moon disappeared like this, we would still have tides. There would only be, bless you, about 30%. Did someone sneeze? It sounded like a sneeze. What was that? Oh, there we go. Our tides would only be about 30% as strong as they are right now because we still have the sun, but they would still be there. Yep. All right, now the depth of the water is also a big factor here. Have you ever watched those documentaries about deep oceans? How weird do the fish down there look, huh? Have you ever seen a picture of a blobfish? Yeah. Yeah, I know. I know. Yeah, they're still pretty ugly. But things down there look different and behave different because of the lack of light and moving water and the sources of food that we do up here. Access to light is a huge factor in the food chain. Why? What's the bottom of our food chain up here? Plants and microorganisms that do what? What do plants do? They photosynthesize. If you live at the bottom of the ocean, can you photosynthesize? No. Their food chain is not dependent upon photosynthesis. They eat each other, but also the bottom of their food chain tends to be chemosynthetic organisms. Those which can survive by deriving energy from ripping chemical bonds apart or making new ones. Yeah, you had a question?
Why do fish at the bottom of the sea have eyes?
Why do fish at the bottom of the sea have eyes? Not all of them do, and not all of them are functional, but if they do, they usually work under very low light conditions. Yeah, but we have light. Not all fish do. As a matter of fact, there are many organisms that don't have eyes that live in dark conditions. I go caving several times a year, right? I go into these deep caves down south, and when you get down, and I'm talking hundreds of feet deep, there are cave scorpions and cave crickets that have evolved without eyes. They don't need them. Yes?
All those fish down there evolved to not have eyes. Would that make anglerfish go extinct? Because their main thing is attracting fish with the light.
Right. That's a huge advantage that they have because of the low light conditions. They have that little light bulb, the anglerfish, and that does attract the animals. Yeah, so animals without eyes that live out there are not attracted to that. Okay, that's a good point. There are species of salamanders, by the way, that also do not have eyes, that live in deep caves. All right. I was in the middle of a point. I don't remember what it was. Oh, photosynthesis is the basis for life up here. Chemosynthesis is the bottom of the food chain down there is what I was saying. Okay, so we have our tidal zone. The tidal zone is the area next to land where water flows in and out during tidal fluctuations. Okay, so it gets pulled out when during low tide and gets pushed back in during high tide. There are organisms that live in tidal zones exclusively. All right, then we have our photic zone, which is as far as the light can penetrate in the ocean. Generally, this is about 600 feet max. It depends on the conditions of your water, though. How cloudy is my water? If it's cloudier, the water is not going to be able to penetrate as high or as deep. If it's really clear water, water can go down up to about 600 feet. That is the photic zone. Most of the animals that you are familiar with thinking about in the ocean live in that zone. Okay? Beneath that, we call that the benthos because it's dark all the way to the bottom of the ocean. Okay? The bottom of the ocean is called the benthic zone. That's where you'll get things like snails and creepy crawlies like crinoids and stuff like that. Okay, your sea slugs. Anything that lives at the bottom of the ocean or can live in the dark is in the benthic zone. Yeah.
So like, could snakes eat human food? Like
No.
they
Mm,
like it's bad for them or something?
that actually depends.
I'm not trying to think. I was just wondering.
Where'd my trash can go? It's gone. That kind of depends on whether or not you count live rats and mice as human food. How often do you eat live rats and mice?
Like twice a month.
Twice a month? Well, then I guess we can say they eat human food if you count that as human food. Could he eat a slice of pizza? No. He doesn't even recognize that as food. To him, it's just another thing. Something small and warm-blooded. He's going to eat it. Actually, so I used to have a snake. I had an albino black rat snake. And I would wear him around my neck when I worked at the scout camp.
That sounds fancy.
Yeah, he was. But one of my favorite things to do to freak out the Boy Scouts was I would put my finger in front of his face like this, and he would like open his mouth and slowly start putting it around my finger. And the Boy Scouts would go, "Oh, he's eating you!" I'd be like, "Oh, what? Oh, hey, knock that off." You know, like just pull it out like that. I shouldn't have done that. That can hurt the snake, but it was really funny. Anyways, okay. So those are the different zones in the ocean. The bottom of the food chain in the bottom of the food chain in the photic and tidal zones is going to be the plankton. The plankton are these photosynthetic animals and plants that live in the water column, the microscopic ones, right? There are lots of different kinds of them. Some of the more famous ones are foraminiferans, which we use a lot in the oil industry because they have a very long fossil record. But what you have is your photosynthetic phytoplankton that photosynthesize to grow themselves and reproduce and make more of themselves. And then you've got your zooplanktons, which are a little bit bigger and carnivorous, and they will eat the phytoplanktons. And then your phytoplanktons get eaten by other stuff, okay? The larvae of fish, for example, tiny little squid, corals, the clams and the snails and the crinoids and the sea anemones that catch them out of the ocean currents and eat them like that. So your phytoplankton get eaten by the zooplankton and the other things that are pelagic. That means that they kind of just like get washed around in the surf, in the ocean. Then we've got our grazers. The grazers are the ones that kind of wander around the bottom of the ocean floor and eat the things that live there. Sea urchins, sea cucumbers, starfish. Those are examples. Then you have suspension feeders. Those are the ones that have kind of like the frills and the fronds that go wash back and forth in the ocean current and catch the swimmers out of it. Okay? So your sponges, your corals, sea anemones, stuff like that. Jellyfish also, by the way, count as suspension feeders because they have their stuff out there catching stuff in the current. They're mobile, but they are still there. And then you have your deposit feeders. These tend to be benthic organisms. They live at the bottom of the ocean. They eat the waste of everything else. Snails are deposit feeders. Yeah, they wander around and eat fish poop. Okay? The waste from other organisms that filter down to the bottom of the ocean, they're going to slurp it up, remove anything organic that they can use out of it, and spit it back out the other end. Okay? They are the recyclers, I guess you could say, of that. And then you've got your larger carnivores that fit in there as well. So your phytoplankton get eaten by your zooplankton. Your zooplankton get eaten by your fish. Your fish get eaten by bigger fish. Your bigger fish get eaten by a shark. Right? All of that. So your benthic organisms are here. And your pelagic ones are the ones that wander and kind of drift throughout the sea currents. All right. One more note on saltwater ecosystems. These are saltwater is the key word there. Salty is relative. It's a relative term. Not all ocean water is equally salty. It varies by ocean and by latitude. Cold water and hot water are going to be not as salty as each other. Okay? Salinity in the ocean varies between 30,000 and 40,000 parts per million. When you're drinking it, when you're taking a taste of seawater, you would not be able to tell the difference. But believe me, it makes a difference to a fish. If you reduce the salinity enough, they will not be able to breathe in that water. That's why if you take a saltwater fish and you dump it in fresh water, it's going to die. And the opposite. You take a freshwater fish and you dump it in salt water, it's going to die. They have adapted to different types of water. Okay? If my water becomes too fresh, the term for that is brackish. So if you're reading any literature or you're doing any research for a discussion board for this class, and you see the term brackish water, think salt water, but too fresh for most saltwater things to be able to sustain themselves in it. Then if it's too salty, it's called hypersaline. Can you think of any hypersaline places on our planet right now?
Atlantic Ocean.
There's that like one ocean that like it's like so easy to like you can't really submerge yourself at all. You just go.
It's on an ocean, but what do we call that? Huh? The Dead Sea. There's a reason why we call it the Dead Sea. Can anyone guess? It's so salty, nothing can live in there. We thought. Turns out, there are stromatolites living at the bottom of the Dead Sea. Stromatolites are those mats of algae that grow into those mushroom shapes, right? Yeah. Some divers finally made it to the bottom. They had to attach a lot of weight to themselves to get down there, by the way, because you are more buoyant in salt water. It's a lot harder to sink. So they had to attach a lot of extra weight, like hundreds of pounds of extra weight to themselves to sink to the bottom. But they found what looked to be stromatolites living down there. Even in the saltiest water on Earth, these things are surviving. No wonder we call them extremophile, right? No wonder extremophile bacteria is so exciting as a prospect for life living in other places, okay? The ability for it to adapt to new environments, hostile environments that nothing else could live in is incredible, okay? But yeah, it's called the Dead Sea because nothing else, apparently, can live in there. I'll show you a picture of that in a second. Yeah? No, there's no source, or at least not much of a source of fresh water into the Dead Sea. There are a few, but not enough to make it salty. As a matter of fact, here, let me show you this picture right now. Dead Sea.
So can I go swim in the Dead Sea?
You won't be sinking.
Salt shoreline, not alt shoreline. Here we go. Look at this. Look at that. Look at how much salt is in there. It's literally piling up and caking on the side of the sea.
So why do we buy salt when we can just walk to the Dead Sea?
They actually do. So they harvest salt from the Dead Sea, from the side of the Dead Sea, and sell it to people across the world. You can buy Dead Sea salt.
Is it better than actual salt?
I feel like it's saltier than salt.
It depends. It really depends. Himalayan pink rock salt is a thing right now because it's got potassium and a few other elements in there that make it nutritionally beneficial beyond just being salt. Dead Sea salt is pretty much just salt, right? Sea salt is just sea salt. It is cheaper over there.
I'm just gonna go break it. Can I just if I went to the Dead Sea, can I just break off a piece of that salt and take it home?
Probably. I don't know. They might have a hard time with you taking stuff from their country. Every time I go to a country and I collect samples and then leave, they give me a hard time. Like when I was trying to leave Iceland with rock samples, they held me at customs at the airport for like 45 minutes. And I kept explaining to them, listen, I'm a geologist. These are for educational and scientific purposes. And they're like, it doesn't matter what they're for, you're stealing from our country. Eventually I had to make them like Google me so that I could verify I am a geologist, I am an educator, that's what they're for. Same thing with, yeah.
I'm gonna just drive a boat.
Yeah, you can Google me.
I'm gonna just drive a boat over there and then
Drive a boat? How do you, it's a landlocked sea, bro.
just get the boat.
You just get the boat.
Over the mountain.
Over the mountain. Oh. He's got one of those land boats, everyone, right? He'll drive that over the mountain. A what?
I see a military game on Church of Joshua Hart.
Yeah, so there was a Joshua Hart who was a Marine. If you Google Joshua Hart paleontologist, I come up.
Ooh, he's on Google.
Okay. Everything's on Google, bro. It's not like a flex.
I'm on it.
I guarantee you are somewhere. Guarantee you are somewhere.
Man, you're on a lot
Oh,
of.
I see you.
Huh?
You're on the news.
Yes, I am on the news. They interview me quite a lot for stuff, yeah. I actually have another interview coming up next week on a totally different subject. Okay. All right. When we're talking about fresh water, what does fresh mean? Okay, you can drink it, but here's the kicker. Fresh water technically means anything with less than 500 parts per million of salt. How many of you like drinking bottles of Dasani? You hate Dasani? I actually kind of like it. A lot of people like drinking Dasani. That's why they still function as a company. Why? They actually put a little bit of salt in there. Just enough that you don't recognize it's salt water, but also enough that you still are a little thirsty after. It's so sneaky. Yeah, they call it electrolyte, right? Because salt is technically an electrolyte, yeah.
You know what makes it efficient when it doesn't like consuming salt hydrate?
It's an electrolyte. Electrolytes help you retain and spread water through your body systems more efficiently. If you are deficient in salt, it doesn't matter how much water you drink, your body cannot send it where it needs to go very well. You need electrolytes to disperse the hydration through your body to your cells everywhere it needs to go, or you could still die, right? Salt deficiency is actually a way that whole communities have died in the past. Okay? They didn't have any convenient access to salt. And they died off as a consequence. So it is absolutely necessary, but they don't really tell you it's there. If you look at the ingredients, like sometimes these bottled drinks, these bottled waters will say electrolyte. Sometimes it'll say sodium added for taste. Yeah, added minerals it'll say. They don't tell you how much salt is in there, which might matter especially if you're trying to watch how much salt you drink, right, or ingest, right? But fresh water technically is any water that has less than 500 parts per million of salt is what I'm getting at here. Now, the history The fossil record of freshwater is not nearly as well preserved as the fossil record for saltwater. Who can tell me why? Everything good over there?
Yeah, he's wrapping himself around the table there.
All right. Just make sure he doesn't put himself anywhere he might get hurt. He doesn't know what'll move. If he goes between the tables and then we bump the table, he could die. All right. Why is the fossil record? Yes.
I forgot exactly what, like how it works, but isn't salt a preservative?
Salt is a preservative, yes. It will actually prevent the hydration of something, okay? It'll absorb moisture, more or less. So yeah, that's why you use salt when you're preserving meat and vegetables and things like that. But my question was, why is the fossil record for saltwater so much higher, so much more diverse, so much, there's more to it than the fossil record for freshwater? What do you think?
What was the question?
That's okay. Why is there so much more of a fossil record for saltwater than freshwater? Hold on. I'm asking her. That's okay. That's all right. Think about it for a second. And then just tell me what your gut instinct is. I'll help you walk through this logic, okay? I just want to know what your gut instinct is first. You don't know? All right. Again, I want to focus on this right here. Let me ask you this. How much saltwater versus freshwater do we have on the planet right now? Which one do we have the most of? I'm asking her.
Saltwater.
Okay. I'm not picking on you to be mean. I just don't hear very many answers from you, and I want to give everyone an opportunity to be involved here, okay? So yes, you're right. We do have more salt water on our planet. Do you imagine that it's been much different from that over time? Do you think there's ever been a time where we have had more fresh water than salt water? We don't have reason to think there is. Principle of uniformitarianism, right? So if we have so little fresh water compared to salt water right now, do you think we would have more saltwater fossils or freshwater fossils in the fossil record? Exactly. That's the logic I'm trying to get at here. Did that make sense, though, how we walked through that logic? Great. There is more saltwater than freshwater now. We can safely assume there has always been more saltwater than freshwater on our planet, which means that there has always been more things living in saltwater than in freshwater. So the statistical likelihood, if it's a 1 in a million chance something in the ocean will get preserved into fossil, and there's a 1 in a million chance something in freshwater will get preserved in a fossil, and the ratio of salt to freshwater is 1,000,000 to 1, we're going to get way less freshwater fossils than we will saltwater fossils. And so we don't have as much of a fossil record for things that lived in lakes or rivers or anything like that. It's still there, just not nearly as plentiful as the ocean fossils, okay? So there is less data that we can interpret with. But there's still enough that we can see that the diversity of life in freshwater is not nearly as rich or robust as the diversity of life in saltwater. Saltwater has things like plankton to form the basis of a food chain. There are way less things like plankton that live in freshwater. The basis of a food chain in freshwater usually is something like algae. And then the algae is eaten by bugs, and the bugs are eaten by fish, and then the fish are eaten by bigger fish, and so on and so forth. The food chain, not nearly as diverse in freshwater. Where did all the salt come from? Oh, good question. Good question. Let me ask you this. What is salt made out of? Salt is made out of salt? What? Sodium and what?
Carbon.
Chlorine. Sodium chloride is salt, right? NaCl. Sodium chloride. It is an extremely easy bond to make because sodium is in which column? And chlorine is in which column?
Oh,
Where's sodium? There's sodium. Where's chlorine? Right, but which column is it in? 7, right? Column 1, column 7. How many electrons do they want in their valence shell? 8. They each want 8. If one has 1 and one has 7, what do they want to do? It's an extremely easy bond to form between two elements that are extremely common on our planet. And so, yes, salt is an extremely common byproduct. And because it's dissolvable in water, a lot of it finds its way into the ocean and there it stays. Good question. I like that question. Where did all the salt come from? It's a good question. Any other questions?
What are some smaller areas of interpretation?
Oh, no. What that means is a lake is not nearly as big as an ocean is, right? And so the likelihood of me finding an ancient lake bed is way less likely than me finding an ancient area that used to be the bottom of an ocean in the rock. We do find the lake beds. As a matter of fact, my master's thesis was all about interpreting fossils found in a fossilized lake bed. But it's a lot harder to find them because they are smaller than the oceans. That's what that means. We have smaller areas that we can interpret that data from. Great. Any other questions?
Lower diversity, what was that like?
Oh, that's just saying that because the lakes are smaller areas, there isn't as much opportunity for mutation and adaptation to kick off. In an entire ocean, which has a whole bunch of environments and ecosystems, you're going to see a lot of change occur. In a little lake, where you have maybe a dozen or 2 dozen different things that live in there, the diversity is not nearly as thick or rich. What else?
The salinity?
Yeah, that's the salts, how salty your water is. Yeah. All right. Good? All right. Well, that's the end of lecture. We can move into lab time now. Huh? Yeah, I'm going to fix that right now. Are there any questions about Lab 3, though? It's pretty straightforward. I give you all the information you need in lecture and in the PowerPoint. I'm not going to go over the PowerPoint unless you guys really want me to, but all the data is there in the PowerPoint. It's a reference sheet for you more than anything. Okay? It talks about each of the different forms of life in a little bit more detail. Do you guys want me to go over the PowerPoint? No? Do you want me to go over the lab PowerPoint? It's a reference sheet more than anything, but I can if you want me to.
I mean, you can. I'm going to go over myself anyway.
Is this similar as this right?
No, this is the lecture PowerPoint.
No, we have the lab.
Yeah, here. Let me just show you. Let me show you real quick.
Oh.
Yeah, it's probably
Okay, so this is your Lab 3 PowerPoint. It's just going over a lot of things that I've already talked about in lecture. This particular lab is about invertebrates, which cover that part of the phylogenetic tree here. Okay, so some fossils that are commonly mistaken for each other. When I have comparison slides like this, it's so that you don't mistake them for each other, okay? Brachiopods and bivalves. Brachiopods have symmetry that is left to right, okay? So when you look at them from the side, those two shells, not symmetrical. When you look at them from the top and bottom, they are going to be symmetrical like this. This way, symmetrical, but not this way, okay? Bivalves, on the other hand, are symmetrical when you look at them this way, when you look at them that way, but not when you look at them from the top and bottom, okay? So, left, right symmetrical, top, down, top, bottom symmetrical. That's the easiest way to tell the difference between a brachiopod and a bivalve. All right? Also, brachiopods were around for a lot longer. They showed up about 541 million years ago. Bivalves showed up about 500 million years ago, which is actually a good note. You're going to have a chart at the bottom of this lab that you need to put X's in to fill in the boxes when these things were alive. You're going to put an X in every slot that those things have been alive during, starting with where they started and ending with where they are now or when they went extinct. Okay? Remember that. You're going to need to use the geological timescale that I gave to you all earlier in the lecture on a different slide, or find one online to figure out what time period 500 million years ago means, or 541 million years ago. Nautiloids and ammonoids. Nautiloids have these very smooth shell segments, which we call sutures, that are pointed towards the opening of the shell. This is where the animal came out of, okay? So a nautiloid and an ammonoid both kind of look like this, where there's like this squid animal that lived in the shell and the tentacles would come out this way, okay? So nautiloids, smooth sutures pointed towards the opening of the shell. Ammonoids, more kind of elaborate sutures that are generally pointed away from the opening of the shell, like this. But they have some undulations to them, okay? Then you've got various types of coral. Rugose corals kind of look like melty ice cream cones, right? Tabulate corals look like a whole bunch of hexagonal columns with bridges connecting them. Kind of looks like a futuristic city where you have a whole bunch of skyscrapers and bridges that connect all of them. Huh?
Like, have you ever seen like somebody put like metal in an ant thing and then they pull it out?
Oh, I see, like the copper in an ant. Yeah, I've seen those.
So is this snake a male or a female?
That's a male.
How do you tell that?
When they're really little, it's hard to tell. The easiest way is the distance between their cloaca and the end of their tail.
Okay.
Yeah. But also when they get older, like he is, the sex organs are pretty easy to see as well. Okay. Then you have a scleractinian coral. This is the type of coral that we have that makes our reefs now. There's a whole bunch of different varieties it can take. This kind of talks about that a little bit. Sponges have a very long fossil record, one of the oldest fossil records outside of bacteria. Okay, and they make these big colonial, almost chimney-looking things when they pull water in and shoot it back out. And they have very specialized sponge animals that are in this colony are specialized to perform different functions as part of the colony. Some catch the food, some digest the food, some spit it back out as waste. Bryozoans are very coral-looking group of animals that have many, many different types of forms. Some look like corkscrews. Some look like the coral that we see today. Some are made that look like fans. They're fenestrate bryozoans like that. They kind of look like lacy fans. Snails, gastropods, include types of snails. Excuse me. Snail shells have not changed a whole lot, other than size, composition, things like that. That kind of characteristic corkscrew shape has been around for a long time, allowing them to retreat into their shells for protection. Belemnoids, these are an extinct kind of cephalopod, very similar to squids. They had that soft body, but inside of their bodies, they had, I put all of them in a box, darn it. They had these aragonite spikes, which look like this. I have some of them sitting over here in a box. I can pull them out if you really want me to. But they look like that. They were inside of the bodies, and this is what provided them ballast. If they wanted to rise or sink through the water column, they would increase the amount of gases in their bodies to rise and decrease it, and allow the weight of that spike to pull them back down deeper into the water. Trilobites are very similar to some of the other arthropods that we have today. So they had an exoskeleton, and they were able to curl up on themselves. I have a few trilobites out in the display in the hallway you can look at, including one that's all curled up. But they were able to curl up on themselves to protect themselves. Okay, so very similar to what pill bugs, or roly-polies as we call them, do today. You guys ever play with these when you were kids?
Roly-poly? Yeah.
Yeah, I used to play with these all the time. Yeah. They can curl up on themselves to protect themselves. This is exactly what trilobites were able to do.
I wish it was really big roly-polies.
That's what these were. Some of these got 3 feet long.
I mean, like now I wish.
Oh, yeah.
Big roly-polies.
Well, I mean, fair enough, but would you really want to be like wading through the water at the beach and then a 3-foot like roly-poly looking monster crawls over your foot. Would you enjoy that, Juliet? No? I wouldn't. I probably wouldn't enjoy that. Play soccer with it? Yeah, sure. All right. Eurypterids were also arthropods, but these were apex predators.
Looks like a sea scorpion.
Yeah, scorpions are descendants from these guys, okay? You can call these sea scorpions if you'd like, okay? They got about 6 feet long. Yeah, these were apex predators in the oceans for a while, okay? Barnacles. Barnacles are attached themselves, they are crustaceans. They attach themselves to whales, boats, docks, everything. We still have these. Actually, their closest relative is the crab. They don't look anything like crabs. What happened here? Evolutionary divergence. Their common ancestor broke into several different descendant branches. One of them became crabs, one of them became barnacles. It has most of the same body parts as a crab. They're just inside of a protective shell that stays in one spot now. Actually, it's extremely hard to remove these. They use an organic cement to attach themselves to objects. If you tried pulling these off of a whale, you would pull the skin off the whale as well.
But like on the boat, don't they use like putty knife looking things to get them off?
Yeah, you can break them off of a boat because you don't care about hurting the boat.
But like an animal, it would
Yeah, it would hurt. It would tear the skin off that animal to remove these.
So then how do they get them off? They don't?
No, you usually don't. However, interesting fact, if you took these into fresh water, the barnacles would die and fall off on their own.
So is that like whales can go in like...
Sometimes they will. Sometimes whales will find rivers and swim up near the mouth of the river so that the fresh water kills the barnacles. Also, that's why places like in Portland, where there's a nearby river that flows into the ocean, they would have giant dock facilities for scraping barnacles off of ships. They would park them there for a while in the fresh water, let the barnacles die, and then scrape off the barnacles.
So there's nothing else that they can get those off of like whales without taking the skin, without going to...
Right, yeah. Insects. Insects have been around for almost 400 million years. They fit in the same category, arthropods, okay? But they're a different group. So they aren't in Crustacea, for example, okay? So this is the largest group in the animal kingdom, by the way. There are more insects than anything else in the animal kingdom combined on our planet. Lots and lots of insects. They've been very successful. As a matter of fact, if we were going to say that the Earth belongs to a certain group of organisms, a certain group of animals, based on numbers alone, Earth would belong to the insects, all right? So insects have 3 pairs of legs and an exoskeleton. Anything with 4 pairs of legs is not an insect, which excludes what? Spiders. Spiders are not insects, okay? Plants. Plants have an extremely long fossil record. They've been around a lot longer than animals. About 850 million years ago is when we can see that they started pushing up out of the ocean. Yeah?
Isn't grass a plant?
Grass is definitely a plant. Well done.
Grass before?
Huh?
There was no grass before?
There was no grass before. No. Grass didn't actually show up until the dinosaurs.
So there was just like dirt that covered the earth?
And other plants. There were lots of plants before grass.
So just everything but grass.
Not everything, but a lot of stuff.
A lot of stuff.
Yeah, it started off with things that look like this, that lived in the shallow water. And then you start developing these flower-looking plants a little bit further out in the land. And then you start getting your trees, and they start moving away from the water. These are all things that I'm going to cover in more detail later on. This is just giving you the brief synopsis, okay? So non-vascular plants until about 425 million years ago. Non-vascular plants needed to be near water. Then we got vascular plants, which were able to pump water up and down through their systems on their own. Like gymnosperms, they were able to move away from the water about 319 million years ago. Then you get angiosperms about 140 million years ago, which are your flowering plants that bear fruit. Those did not exist. There were no flowers, no flowering plants until about 140 million years ago. Grasses didn't show up until 129 million years ago. Before that, where we have grasslands now, you would have had something more like a fern land, covered in a vast expanse of ferns. Okay? Now we have grasslands that fill the same niche. So there's that word. They fill the niche that ferns did before. Okay. So that's the PowerPoint here. It has all the dates that you need to know. It has how to tell apart the fossils that you need to know. It has all of that. Any questions? All right. Well, I'm going to end the recording here and pick up on Thursday.